My name is Mitali Gautam, and I will be talking to you about my research on setting up the boundary conditions for the late Permian early Triassic interval using the community Earth system model. Now, we've often used the past climates to understand the evolution of future climate. And so one of such important events in the past is the Permian-Triassic interval that took place about 251 million years ago, and that faced one of the major mass extinctions of Earth's history, where about 90% of marine species and 70% of terrestrial species went extinct. And so of the many proposed triggers, the eruption from the Siberian traps is the most accepted one, which basically could have led to emissions of sulfate, carbon dioxide, and so on, that basically led to the terrestrial and marine extinction. Now, we know that the conditions in the past are significantly different than what they are right now. And so the goal of this paper is to set up the boundary conditions in terms of what the conditions for geography were, what the conditions for vegetation cover were, and so on. So basically the land surface characteristics, as well as changes in the radiative forcing to test the sensitivity of the climate, essentially trying to represent the various scenarios that could have led to such transition into the hothouse world. And so the model that we use here is the community Earth system model. And so it has various components that interact together with the central coupler. As a part of my methodology, there are two parts, that is incorporating changes in the land surface and then incorporating the changes in the radiative forcing. Now, as you can see, starting with the changes in the paleogeography, it is a synthesis of 3 studies, and so the newly constructed topography with various changes is a synthesis of these 3 studies, which is also based on the scientific evidences like the fossil data, the geologic and tectonic data, and so on. Following the paleogeographic changes, the changes in the vegetation cover map, it has been reconstructed using the past model results. And so this past model result that you see was in terms of the climate zones, which was adopted from Rees et al. And so those climate zones, since we need to input in the model, we basically translate those in terms of its land surface types as well as the plant functional types as per the model. And so the translation follows as it is shown in the table over here. Now, pertaining to the various vegetation types, we also changed the soil albedo values or the soil color values. Basically, the scale ranges from 1 to 20, 1 representing the lowest albedo, that is the highest reflectivity, and 20 representing the lowest albedo, representing the lowest reflectivity. And so the translation follows in terms of what is the major soil type. For example, in desert-like regions, we know that the soils are lighter, and so that would have lower values for soil albedos, and the organic matter-rich soils will have darker colors, and so on. In addition to that, we do want to create the boundary condition files for the river runoff and tidal dissipation in future, but currently creating the files for aerosol forcing, where we prescribe a spatio-temporally different aerosol is shown over here. And so you prescribe a non-uniform aerosol as well as various concentrations of carbon dioxide to see what possibly were the combinations or the reasons, the factors that could have led to such transition into the hothouse world. And so such effort can help us in understand the feedbacks that involve such hothouse climates, and these can serve as robust tools to address the shortcomings in simulating the climates for future that lead to such consequences. I'd like to thank my advisor and my coworkers. I'd like to thank NSF and NCAR for the support. Thank you so much for listening in. Have a good one.